Yo, what's up, guys? Welcome back. Episode 54. Um, yeah, I have to leave in about 45 minutes. Well, I don't know, yeah, kind of like 50 minutes maybe, I don't know, 45, something like that. Anyway, point is that we're going to do a little bit of a 45-minute portion here. Probably do a couple problems, we'll see what we can do. And then I'm going to finish the later portion later today after I come back from the test. So probably going to be dark outside when I come back and finish this video, but it'll probably be like 6, 7 p.m. So probably just do like maybe a question or two and then probably end the video. So so we're going to get started here. So our Pokemon of the day, I think that's number 54. We got a Psyduck today. Another classic Psyduck. Let's listen to the sound, shall we?
Psyduck,
Psyduck, Psyduck, Psyduck, Psyduck. I don't even. She loves Psyduck. She loves the video on loop. Nice. She loves Psyduck. Let's go. Yeah. I think what we're going to do this morning is that we're going to kind of revisit like a couple problems. Kind of see kind of where we've kind of evolved a little bit. Maybe we can come back and take a look at some problems that, we've solved in the past. So I think what we're going to do is maybe we'll do... trying to think. Sliding window problem, probably a couple linked list problems. We'll do one linked list problem. I think the most important linked list problem to me, I mean, I think I'm pretty confident about doing most of these, but we're going to go back to the classic of reversing a linked list. I don't want this to show code. Okay, no, it doesn't. Okay. So we're going to start with this. We're going to simply reverse a linked list here. Just to see if we can kind of do this off the top of our head. And again here, like, we're going to kind of just look at our nodes here, like, just kind of remember what we have to do here. Obviously, I'm feeling confident about this question. I think this is pretty easy solve for me nowadays, hopefully. I want to make these bigger so I can... Let's make these bigger, a little bit more clearer. Feeling good today though, like I'm feeling like my brain's on check right now, so hopefully... Okay. So what we're going to do here is we're going to create a... we're going to make our... Oh, sorry, I'm so itchy. Okay. I'm going to make our cur equal to head. I'm going to make our previous is equal to none. I'm going to look through cur. So while cur does not equal none, right, we're going to that means we got to redo this. Oh my gosh, we got so many. Some jam on here or something. And I'm going to clean up this jam on my mouse really quick. It's kind of frustrating. I'll be back in a second. hurt my head. Okay. All right, that's better. Let's take a look at this problem now. Okay, so we got while is equal to none. We want to create our next is equal to code.next, right? Gonna have to redo this again, bro. So frustrating. We got our prev here, right? Then we got our 1, our 2, our 3, our 4, now 5. Okay, now really to think about this, we use our while loop here and we create our, well actually technically here, this is not equal to anything yet, right? So we have our prev. We want to create our next. So our next is here. Right. We got our cur is here. Right. We got our next here. And we got our. I guess this shouldn't really be prev. This should be, I guess, none or null. Get rid of this, make this more accurate. I guess this is null here. Let's just put null. And we got our prev is equal to here, right? So we did our next. So now what we want to do is we want to our code on next is equal to prev yeah, we want to do well. Our code on next is equal to prev, right? So what we did here is that we switched around this link here, made this go here, or this go here, sorry. So we want our cur is equal to next, right? Sorry, no, our prev is equal to cur. And then our cur is equal to next. Yeah, our prev is equal to cur, our cur is equal to next. And then I guess we just want to return prev. I think that should be good. There we go. Easy. Easily reverse the linked list. Okay, sweet. Let's take a look at like some sliding windows. Sliding window. Okay. Give us some questions. Sliding window. Oh, jeez, 147 problems. Jeez, man, there's a lot of sliding window problems. I didn't think there was this many. How about maybe we just find all anagrams in a string? Check out this one. I don't know. Okay. Find two strings S and P, return an array of all the start indices of P's anagrams in S. You may return the answer in any other. Substring will start index 0 is CBA, which is an anagram of ABC. Substring will start index 6 is BAC with an anagram of ABC. All the start indices. Okay. So I'm trying to think here. Well, AB, we got BA, and we got AB, right? Yeah, okay. Okay, I'm going to solve this with a sliding window. I think should be the way to do it. So if we do P, where we got starting indices of P's anagrams in S. So I guess, well, let's create our left pointer, right? And create our length, because the length is the length of the substring that we're looking for. The length of P. So right in range length S. Okay. How do we want to do the sliding window, right? So if we do, well, we could do, well, we could kind of use an array as a window. I think maybe using an array because we can easily index it. So how about we create a current array, right, to track our current window. We'll call it per window. For right in range length S, we check, well, if S right equal to count 0. Sorry, count left. No, this is not the right way to do it. We want to loop right. If S right, that's not really a sliding window, right? Because we're using our left pointer. Is that considered a sliding window? I don't know. Original letters exactly once. Can we use an array? I don't know. What are we gonna look for here? Maybe if we get a little paint going, get our mind going, blowing. Get our mind blowing. CBA. C B A E B A B A C D. Okay. So we're obviously looping right. Correct. Looping right. So if our guess we can do, well, if left in, no, sorry, if man, I generally don't know how we can do this. Like, we're gonna need a while loop of some sort. That's right. In P. If it's not in P, then what do we want to do? Well, that's right, not in P. Left plus or equal to 1. The increment left, right? Well, if that's right. Fuck. My freaking ear's bleeding, dude. Ow. Ow, bro. That's right in P, so man, I'm trying to think about this. Like, I don't think that's correct. if s right, the length of current window is equal to the length and p in current window. Then we want to do one current window window.0 pen. Change this to res. And this else, if it isn't, then I don't know if that resets it. Maybe it does. There's definitely a better way to do this, bro. Like, for sure. Like, there's definitely, like, a better way to do this. Whoops. Current window. I guess we don't really need this. Current window append, that's right. Well, the length current window is greater than the length then we need to go window dot plot. Moving leftist character. Or if the length of current window is equal to the length. Okay. Sorted co-window is equal to sorted P. Then res append left. Okay. window is equal to the length, then length plus equal 1. I think I was just thinking about it correct, but I just little things, man. Increase that point. Check if it's the same. And what we just want to return. Res out of handler. Independent first character. I guess we just return res. We'll accept this solution though. No, it did not. It's too slow. Time limit exceeded. Because we're sorting it every time. That's O(n) squared. Okay. What would be a better approach then? Maybe we're gonna do something without per window. So, sliding window plus hash table. Oh, sliding window. That's fine. Easy to understand with simple code. What is he using here? Okay, they're all using dictionaries. Okay. So apparently, p underscore count is equal to counter p. Yeah. S underscore count is equal to counter, and then apparently we need to slice this. So we go. Let's do the res. Let's move left down here. Get rid of this. I want to see. Give a return here. Let's get rid of that. I want to print p underscore count and print s. Okay, so oh, you stretch, bro. okay. What we want to do here, we want to loop well, right in range, and then we want to start from I guess the same as this here. Length p minus 1 into length s. Is that correct? Oh, yeah, length p. Okay. We want to check well. Yes. Nice, and let's go count. S underscore count. S right. S count S right plus or equal to 1. What does that do? We're referencing S count dictionary. S right plus or equal to 1. We want to check the length. Well, check it. Think it's the same. So S, if S underscore count is equal to P underscore count, We want to do res.append s count 0. Res.append left. Oops. S underscore count s left is equal to 0. Then we want to delete s underscore count s left. And I guess we just want to increment left. Return res outside of the for loop though. Interesting. I just don't understand here where it goes for right in range of length p minus 1 like this. I got that where it's starting from, but then s count s right plus e1. What happens if s right doesn't exist in s count? You know, like. Okay, I didn't know that. So apparently the counter class here automatically initializes it to 0. That's interesting. Okay. Okay, we're repeating the starting window. Interesting. Okay. Interesting problem. Sweet. Okay. We're gonna call it here. We'll be back probably later tonight, and I don't know, probably in a long day, 7 or 8 hours. So we'll probably do a couple more problems after that. Then we'll call it a day. Appreciate you guys. I will see you in a second. Hey guys, we're back. 6:53 p.m. Well, like maybe 8 hours later. Yep, gonna do another problem. Jeez. My leg. Do another problem. Maybe a couple more. Let's take out a hash table problem. Let's do a little easy one. Uncommon words from 2 sentences. And then we can move to like a binary tree problem, we'll call it probably. Hopefully this is a pretty easy, quick one. Let's take a look. A sentence is a string of single space separated words where each word consists only of lowercase letters. A word is uncommon if it appears exactly once in one of the sentences and does not appear in the other sentence. Given 2 sentences, S1 and S2, return a list of all uncommon words. You may return the answer in any order. Okay. The word sweet. Separated by a single space. Okay, so the way I'm kind of thinking about this problem, Obviously, I feel like this is a hash map problem, but here I think we'll have two hash maps, which would be like s1 underscore map, then s2 underscore map, right? Pretty much what we're going to do is we would we create two maps, and then we would compare, well, we'd compare each different key in map 1, right? And if it doesn't exist in map 2, then we'll add that to our res list, right? And then we'll do the same for S2. I think that's probably what we're going to do. Yeah, so let's create our dictionaries. I think that's probably the most optimal way to do this, which would be an of and solution. We create our res array here that we're going to return. First of all, we got to see, well, how we're going to be able to split this into these words to a hash rate. Could we use a counter here? Probably not. I don't think so. I think a counter is probably just for characters. Alright, then well, we can use a counter. So we can do here, but we can do counter s1.split counter s2.split. I think here if we print s1 underscore map and we print s2 underscore map, nice. Interesting. Okay. So yeah, we pretty much use the counters, right? We got our res here. So now we want to check, well, for key value in s1 underscore map dot items, if key not in s2 underscore map, then we just add the key. We do res.pen key. We do it for s1. And then we do it for s2. So key value in s2 underscore map dot items. Key not in s2 underscore map. Do res dot append key. And pretty much we want to turn on res. I'll put Apple. Why isn't this one outputting properly? Key value in S1. Oh, whoops. Okay, we did that. Now we need to do and s2 underscore map and value is less than 2. The value is less than 2. There we go. Simple problem. Nice. Okay, let's check out a binary search tree problem. See, I feel like these are tough problems, I'm not gonna lie, but I feel like I'm gonna eventually really like them. I think. Let's do this one. Because I feel like they're all the same thing, you know, it's either like, you know, okay, is it DFS, BFS? If it is DFS, then, you know, in a DFS problem, you can have an iterative or a recursive solution. You know, and then you have post-order, pre-order. What's the other one? Post-order, pre-order. Techniques, post-order, pre-order, and what for DFS? In order. Pre-order, in order, and post-order. Pre-order is root, left, right. In order is left, root, right. Post-order is left, right, root. And then BFS, really, you can only have an iterative solution, I think. Obviously, you know, I think you can do it recursively, but I think it's mainly done in an iterative way. I don't know. Anyway, let's take a look at this problem. Given the root of a binary tree, the depth of each node is the shortest distance to the root. Okay, return the smallest subtree that it contains all the deepest nodes in the original tree. A node is called the deepest if it has the largest depth possible among any node in the entire tree. The subtree of a node is a tree consisting of that node, plus a set of all its descendants of that node. Did I do this? Didn't... Oh, I think we didn't solve this problem. Maybe we're going to come back to it. Okay, stuff this problem. Let's do a different one. Let's do some root to leaf nodes. You're given a root of a binary tree containing digits from 0 to 9 only. Each root to leaf path in the tree represents a number. For example, the root to leaf path here is 1, 2, 3, represents number 1, 2, 3. Return the total sum of all root to leaf numbers. Test cases generated. The answer 32. A leaf node is a node with no children. What? How did they get 25, dude? Like, what? This is definitely an interesting problem. So here it'd be 495 plus 491 plus 40. Yeah, and 10, 26. Okay. Well, I definitely think this would be a DFS approach. So, you know, we'd loop through these numbers. And each number we pop, well, I think this is definitely going to be a recursive solution as well. I think. I don't think you can do this iteratively because we're going to need to, right? I'm trying to think here. Oh, we go 495. They have a okay. Okay. Def DFS, passing out root. Our base case, then we would need DFS root. You can save all answers in an array, I guess. Res is equal to this. What am I thinking is the best way for this? So I definitely think the best way for this problem would be we look to each value and we kind of build a string to each value, right? And then if we see two nodes, then we append that string to res, I think. I don't know if you can do this though. I think that's going to give it a space straight away. Oh, if not, no dot left. Or if not, no dot right, then we'd append, well, because we want to check all, we want to check either, because either or both doesn't matter. Like, if there's an empty node, then we want to return what it is. We would return res.append okay. I guess we can async right, then what will we do? Well, if no dot left or no dot right. Okay, if no dot left. Plus or equal to okay, let's think about this. If no dot left, then we can run the DFS function. I don't know if this. I doubt this will work, but well, we want to return res. I don't know if the solution will work. Probably not, but if not, no, the left. Oh, this is recursive. Let me get rid of this if right here. Let's take a look. Incorrect base case. Okay. What do you mean append this at leaf nodes, dude? We were close. We were close. Yeah, we were close. Kind of frustrating. Technically, we don't need this. Real close. I mean, if root.left, node.left, we have cur. Get rid of this. We had the right thinking. If leave node. I mean, I had the right thinking here, you know, if not node to left and not node dot right. Oh, is it? Oh, specifically only a leaf node? Okay. Okay, so this needs to be and. I didn't think it had to be a leaf node. Okay. Alright. Do we do this right? Append. I'm going to cast this into an integer, return it, and then outside of here we want to do cur plus or equal to string node.val, and if not root, return. So if root is nothing, we just return. We return res. Build our string per node.val. We were close. I mean, we had the right idea. It's okay. Like, no, not defined. Whoops. Oh, should return res. We need to return well. Return for string comprehension. What is it called, man, in Python? Jeez. String comprehension, string list comprehension? Bro. List comprehension for lists in Python allows you to write size one-liners for loops inside functions like return, sum, already. Okay. List comprehension, string comprehension. That's what I. List comprehension, bro. Oh my gosh, dude. Yeah, new list expression for item in iterable if condition is true. Okay, yeah. But here, I mean, we can easily just do a for loop right here. You know, do a for I in res. And then, you know, create an answer out here. And is equal to 0. We can do, well, ands plus or equal to I. Just return ands. I think that should work. Yeah, but in this case, from the internet, we can just return the sum of res. Thank God we're using Python. Easy things like this. Let's get rid of this ands right here. I like that problem. That was a good problem. Like, curious, can we do that problem iteratively though? Can you do 129 iteratively? I'm sure you can, like, obviously, but I'm going to submit that. Nice. There's obviously a fast solution here, so I assume that is the iterative-based approach. I guess we can do that really quick. Let's take a look. So why not? Let's create our stack here, and we do while stack. I want to put in our root here. I guess we want to pop from our stack, so we do node is equal to stack.pop. We pop. Now, what do we want to do with this node? Well, we need to check. We need to add it to our list. Let's build our string. Alright. I guess we can have, well, I guess cur is equal to this. We can do, well, cur possibly equal to string node.val. Then we want to check, is it a leaf node? So how do we do that? Well, we do, well, if not node.left and not node.right, then we want to add this. So res.append res.append cur. I guess cur is equal to oh. Total sum is 0. Times 10. Why is it times 10 here? Why is it times 10, bro? Okay. I guess we can have a res right here, right? Node is equal to stack.pop. No. I guess cur. Is it a leaf node? It is. Res.append current. if no dot left, stack dot append, no dot left, current, if no dot right, stack dot append, no dot right, current. After we got to the while loop, we want to return sum of res. We're not actually adding a string, build a string. Okay. String with a val. We want a pending integer occur. Why isn't this working here? Oh, we need to the double parentheses, baby. Can't forget. Let's go. Ooh, 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 ooh. There we go. Beats 100%. Nice. Simple. Use solution. Iterative. All space complexity here is O of n. And n squared, I think. Right? Is this a what is this? I think this is a O of n times O of n squared space, I think, because it's stacking the O of n plus h. Okay. Let's just do O of n plus n. Stretch approach. Iterative DFS approach using stack. Let's get rid of this. Let's do please upvote. Post. Nice. Cool, 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 cool. What are we at now? We are at 212 problems solved. 97 medium, 110 easy. 5 hard. Nice. Cool. Feeling good about those problems. Felt kind of good to solve those. Yeah, we will take a look at some more tomorrow. So I appreciate you guys watching. See you later.